the activation energy, Q, for aluminum in a copper solvent at 575 degrees Celsius is 1.6 times 10 to the 8th joules per kilomole. If the diffusion coefficient D is 9.75 times 10 to the negative 16 meters squared per second, the constant of proportionality D naught is most nearly. Okay, so you're going to need to use, hopefully you've got all of this on your handout, so because I don't think I can show both of these at the same time. Be a little bit like I'm going to have to cover something up, but you're going to need to use this equation. You're going to need to do some manipulation. One thing I'm going to point out to you is making sure that you're looking at your units. Okay, this is mole times Kelvin. This is kilomole. Okay, so remember Kelvin being a way to a difference from degrees Celsius, and you can find some information about converting from degrees Celsius to Kelvin at the very beginning of your reference manual, or you can just search it for now. So that's something else you're going to want to do too. Okay, great. Okay, so way to approach this problem, the way I would approach this problem is to go ahead and come up with what's been given to you. So we've got our givens, and so I'm just going to let you take a look at that. So we've got our formula that I'm just grabbing off that other page. I'm rearranging it because of the variable that I'm solving for. And then I'm writing down all my givens. So I know that the diffusion coefficient is that 9.75, etc. I know that temperature is in Celsius, but I'm going to need to get it into Kelvin. So I'm going to have to add that 273 to get that temperature into Kelvin. I know that ideal gas constant given to me, and given that Q. So those are the things that I know. I noticed that I'm going to have to deal with Q and divide it by R at some point here, and I can see that Q is in kilomoles and R is in moles. So I'm going to need to do some conversion there. I could do it in the equation. I can do it before. I'm going to do it before. So I'm going to go ahead and convert that Q from joules to kilomole to joules per mole. So let me show you what that's going to look like here. And like I said, I've got these slides, so I will send them to you after. I'll just send you the kind of final one here. So Q is this 1.6 times 10 to the 8th. I know that there's 10 to the 3 moles in a kilomole, so I'm going to reduce that basically, and it becomes 1.6 times 10 to the 5th for Q. And then I can plug that on into my equation. And so when I do that, I just want to make sure that all my units are going to cancel out. So this is kind of the final solution page, which I will send to you at the end of class today. So I didn't write everything out, but basically we have the D in meters squared per second. We're dividing that by E to the, and then my units for Q are joules per mole. My units for R are joules per mole degree Kelvin, and then I'm multiplying that by degree Kelvin. So my kelvins are going to cancel, my joules per mole are going to cancel, so I'm winding up with the meters squared per second, and so my number does wind up to be 7 times 10 to the minus 6 meters squared per second. So A was the answer I was looking for there.